Welcome back to this course on polymer chemistry, and today we are going to move from our discussion on step growth polymers to chain growth polymerization, and we will begin with radical chain polymerization for about 4 to 5 lectures, followed by ionic polymerization and other types of chain polymerization later lectures. In this lecture, we are going to cover general features of chain polymerization, which we will basically revisit from our introduction lecture, and then we will talk about feasibility of chain polymerization, how the structure of monomers determines which type of initiator we should choose, and different modes of propagation of a free radical in a free radical polymerization, different types of initiator and initiator efficiency. Now, let us revisit the discussion we had on chain polymerization in first two lectures during introduction. What are the general features of a chain polymerization process? In the step polymerization, we have seen that we need at least two functional groups, so that the reaction can happen between the functional groups, but in case of chain polymerization, we need one functional group, monofunctional group. In most cases, it is a double bond. We can do polymerization, chain polymerization with more than one functional group as well, but then in that case, like the previous case of step polymerization, it will give cross linking in the polymerization, not a complete linear polymerization. So, if you have only one functional group, in this case a double bond, it is sufficient to give you a linear polymers. Now, polymerization, chain polymerization are in general consist of three steps, three main steps: initiation, propagation and termination. In initiation step, a reactive species R is formed from initiator molecule I. This reactive species then react with a monomer, gives you a chain initiating species. This will initiate chain by reacting with further monomers, forming extended chain, and this will progress to make a complete polymers. So, this is part of initiation steps, this is propagation steps, and also we have termination step. We also have another step, another possible step like transfer reactions, which we will discuss when it necessary. So, in this case, you require a reactive species to initiate the polymer chain, unlike in step polymerization where you did not require a reactive species, and depending on this nature of this reacting species R plus, you can classify this chain polymerization reactions in different types. For example, if the R star is the reactive species, in this case is a free radical, then we name this reaction or polymerization as a free radical polymerization. If this is a cation, then it is a cationic polymerization. If this is an anion, then it is a anionic polymerization. Chain polymerization could be other types as well. For example, polymers using other type of catalyst like Ziegler-Natta catalyst, and also it could be different other types which are not the majority or a major class of chain polymerization, but they also are part of the group of chain polymerization. For example, ring opening polymerization, group transfer polymerization, and so on. We will talk about these polymerizations when in a later lectures briefly. We will come back to the general features of chain polymerization. We by this time we know that we can build linear polymers in chain polymers from a monofunctional group. Then chain polymerization usually consist of three main steps: initiation, propagation and termination, and usually there is no loss of molecular fragments. Like in case of step polymers, we had small molecular condensates were coming out during polymerization process, but in this case there is no loss of fragments. And we also know from our original discussion that we do not require high conversion, unlike a step growth polymerization where we require a high conversions to have a high molecular weight. In this case we do not require a high conversions to build a high molecular weight. If you recollect from the discussion we had in the first two lectures, that in case of chain polymerization the molecular weights builds very soon, and then it says at very low conversion itself it builds very high molecular weight, and the molecular weight remains as high, at very high during the conversion. There are some other things might results in change in this nature of this line at very high conversion, which will come back in the appropriate time. So, in this case we have seen from earlier case as well, an earlier discussion as well, that at a very low conversion itself molecular weight is often is high, and as the time progress more and more number polymer chains form, and but the molecular weight remains more or less similar, which is very high. Now, in this polymerization chain polymerization, monomer is present throughout, but its concentration decreases gradually or steadily. And we also know that during this chain polymerization we have only monomer or high molecular weight polymers. We do not have this intermediate molecular weight oligomers like in step growth polymerization. We have either monomer and high molecular polymers, and also have these initiator molecules and solvent if required. This chain, in case of chain growth polymerization, a chain grows only by addition of the reactive species or the monomer at the end, at one end of the growing chain. If the polymer progress, then a monomer is always added at the end of the polymers to grow the chain further. And these chain reactions are typically have very high exotherms and low activation energy. And if you just think little more about the mechanism of this chain polymerization, typically you have a pi bond is converting to a sigma bond during this chain polymerization, or which is starting from a double bond. Now, this is having a definitely having a exothermic nature, this reaction, and we also know that, we also can imagine that when the monomers add on to form a high molecular polymers, the translational entropy decreases. So, in this case the entropy change is also lower. So, if you think about the thermodynamics of this chain polymerization briefly at this moment, because this is exothermic negative and this is also negative. So, there is a competition between these two terms, and in normal temperature, typically the reaction temperature, there is the temperature where we do reactions, this dominates. So, the reaction, this chain polymerization are thermodynamically feasible, in most cases or not. This del G is less than 0 for the typical temperature where we do reactions in the lab, which means that most of these double bond containing monomers should polymerize given its thermodynamic feasibility. But if you think the kinetic factor, not every monomer containing double bond can be polymerized with every type of initiator. That depends upon the structure. The initiator which is best or which can polymerize a monomer containing a double bond will depend upon the monomer structure. For example, if we take a simple monomer, so we take a very simple monomer like this, where Y is a substituent. Now, the feasibility of these monomers to undergo polymerization, chain polymerization by a radical or a cation or a anion would depend upon the reactivity of this double bond and also the stability of the species which formed due to reaction of this monomer and the reactive species R star, which we talked about in the last page, which in turn depends upon the inductive effect and the resonating effect of this substituent group Y. For example, if I have say Y as a electron withdrawing group as nitrile. So, if I consider a molecule like this CN. Now, it is a electron withdrawing group, which means that because this is present, the reactivity of this double bond towards a electrophile increases, and also if there is an anionic charge here which can be easily stabilized by the resonating effect of the nitrile group. So, if I have a anionic species reacting with this monomer, it will form, for example, say CH2 . Now, it can stabilize and form like this. So, this is this monomer acrylonitrile will be very much feasible, reaction of this monomer will be feasible by a anionic initiator. So, it can undergo chain polymerization by a anionic initiator, because you have a electron withdrawing group which actually increases the reactivity of this double bond towards the electrophile, and also it stabilize the reactive species which formed because of the reaction of this monomer with the reactive species. But if you have a cationic initiator for this case, now if you have a, this was an anionic initiator, if you have a cationic initiator for this case, then if it has to react and form something like this. Now, this will not be stabilized by these substituents. So, these monomers will not undergo a cationic polymerization, it will only undergo anionic polymerization. Now, if you have a radical, for example, if you have a radical initiator, then it will form now this can also get stabilized by this process of resonance, okay, which means that this acrylonitrile monomer can be polymerized by a anionic initiator and a radical initiator, but not by a cationic initiator. We will take some other example. For example, we have a monomer like this. It could be a aldehyde group, the substitution could be aldehyde group or a say ketone or a acid or a ester or a amide like this. So, it could be any of these groups. Now, when these monomers undergo a anionic polymerization, it will form a species like this. Okay, it could be any of these species which we wrote here. Now, in this case also this can get stabilized by resonance and this will form this. So, this is also another set of monomers which can be easily polymerized by a anionic initiator. Similarly, this can be also polymerized for a radical polymerization, because again this like the earlier case, this can undergo resonance and form this. Okay. So, this type of monomer which contain this set of, there is a carbonyl group here, they can easily undergo anionic polymerization, they can undergo radical polymerization, but like the earlier case they cannot, this set of monomers cannot undergo a chain polymerization initiated by a cationic species, because then if you have a cationic group here, it will not be stabilized by resonance. Now, if we talk about this monomer, now this monomer, if I polymerize with a cationic initiator, then it will be a cationic species. Now, again this can be stabilized by resonance like this. So, if you have a monomer like this, then it can be polymerized by a cationic species. Anionic? No, it cannot be polymerized by cannot be polymerized by anionic species, because if you have a strong electron withdrawing group here, so anionic cannot be. If you have a resonating group here which is electron donating, electron pushing, so it cannot stabilize a anionic group here, even if there is a weak electron withdrawing group of electron effect of this OR group by inductive effect. Now, if you have a monomer like this styrene, if you have a monomer like styrene, then what happens if you have an anionic case? You have other resonating structures. If you have a cationic, and so a radical. If you have a radical group, then it can also be stabilized by this substituent group. Okay. Now, if I have a if you have a monomer like styrene, you can see that in each of these cases, anionic, cationic and radical, the reactive species which is forming because of the reaction of the monomer with the previous reactive species can be easily stabilized by a resonating structure in all the three cases. So, styrene is example where styrene can be polymerized either by anionic, cationic or a radical group as well as a radical group. So, these are the examples how the structure of monomer will determine whether it can undergo chain polymerization by anionic species, anionic initiator or a cationic initiator or radical initiator. And we have seen the examples of several monomers, and let us see the table and we sort of summarize whatever we have just learned in last 5-10 minutes. So, if I have a simple monomer like this, if I can have Y as COR, then we know it's can be polymerized by both radical and anionic. It cannot be polymerized by cationic. If you have a acid or ester or amide, it can also be polymerized by radical and anionic. If you have a nitrile, again it can be polymerized by radical and anionic, not by cation. For example, if you have a substitution as a phenyl group, a styrene, case of styrene, then it can be polymerized by all three. And if you have another double bond hanging from the original double bond, then also it can be stabilized by any of these three mechanisms, anionic, cationic and radical. So, it can be polymerized by all three mechanism. We just seen that if it is a ether, then it can be polymerized by cationic. It can be difficultly polymerized by radical also, but the most preferred choice of polymerizing a ether group hanging from a double bond is to use cationic polymerization. If it is a halogen, then its halogen is having a weak inductive effect, electron withdrawing inductive effect, and weak electron donating or electron pushing resonating effect. So, because both these electron donating and electron withdrawing strengths are weak, so it actually does not get polymerized either by anionic or cationic. It only gets polymerized by the radical mechanism like vinyl chloride and for example. So, now there are other possible substitutes you can imagine, and depending on the chemistry behind it, you can find out or you can decide whether which one to try out first, which is the most easiest way it can get polymerized. And if it is can be polymerized by radical, that is the most easiest way of polymerizing polymer process of these three. So, we come back now only to radical polymerization. Radical polymerization, we are talking about the chain polymerization and different structure and different initiator. Now, we start solely on radical chain polymerization. So, what are the types what are types of monomers can be used for radical polymerizations? Monomer containing double bond between carbon atom. The examples we have just seen: ethylene, styrene, butadiene, isoprene, etc. And if the monomer containing electron withdrawing group, then the polymerizability of that double bond actually goes up, because the reasons we just talked about in last 10-15 minutes. So, examples like methyl methacrylate, acrylamide, vinyl chloride, acrylonide, vinyl acetate, etc., can be easily and very easily polymerizable by a radical initiator. Now, what are the monomers? It is difficult to polymerize or cannot be polymerized at all if there are more substitutions with both the carbon atoms. In the example we said, just showed in the last pages, where you have CH2 CHY instead of one substitution. If you have substitution in both the carbon, then it becomes more difficult. For example, if you compare between 1 butene and 2 butene, it is easier to polymerize 1 butene than 2 butene. And if its substitution is bulky, so like if you have a diphenyl ethylene, 1,1 diphenyl ethylene, then it is very difficult to polymerize, and if you have tri substituted or tetra substituted, then also it is very difficult to polymerize. So, if I want to summarize just plain structure instead of substitutions, if you have no substitution, it works fine in radical. If you have mono substituted, it works fine, except the case where it is CH3 for propylene. We will come back why it is so. And if you have disubstitution in single carbon, and unless they are not bulky, it usually work. If they are very bulky, then because of the steric reasons they do not work. And now if from here, if you go for more and more substitution, the reactions become more and more difficult. Like this is very difficult, and these two tri substituted and tetra substituted almost never works in a radical polymerization. So, what in the case of this allylic monomer, for example, the propylene we just mentioned in the last slide. If you have radical, then it can react with a propylene to form by a initiating chain initiating species release, which can react with the other propylene monomer and progress the chain or propagate the polymer chain, and this can be stabilized inductively by this. So, there should not be any problem in that sense. But if you compare the other alternative, which is shown here, if this R dot abstract a hydrogen from a neutral species RH, then you have this radical species generated. Now, which is even much stabler than the previous case, because here in this case it is stabilized by resonance. So, in most cases this reaction dominates than these reactions. So, this is one of the cases of transfer. So, this is for these reasons this propylene is difficult to polymerize by radical, and this does not happen if you have say monomer like methyl methacrylate, where there is not possible, this possibility does not arise. Okay, now how if you have a monomer like this CH2, again come back to that very simple monomer. Now, this can react with R star can react on this carbon or this carbon. If it reacts with this carbon, then it forms okay, and if this reacts with this carbon, then it forms something like this. Now, how does it propagate? This can react with either of these two carbon in terms of possibilities. So, if it react with this, then it forms if this react with the other side, then it forms a species like this. Now, given these two structure, now the fact that this monomer is reacting with this reactant species, which means that whether this radical or a cation or anion will get stabilized by the substitution Y present. So, it is always given this and this choice, because the presence of the stabilizing group Y as a substituent, this reaction, this side is always preferred, unlike not this. So, approach of R to this carbon is always preferred over this carbon. Now, if you have, so this is dominating, or this is almost exclusively formed compared to this, okay, because of the electronic stabilization of the Y group. Now, this can, for the same reason, this is preferred compared to this, and here it is an additional factor that you have a group, the approach of this, if it is approach from this side, it will be even sterically hindered. So, it is approach from this carbon is preferred both electronically and sterically. So, if I write this side as head and this is tail, then finally we get a polymer which has in head tail arrangement. Okay. So, in chain polymerization, you have finally when the polymer formed, you get a head tail arrangement, not any of this. If whether it is a head or tail does not matter, you can have a tail head arrangement as well, does not matter, but it is basically alternate head tail type arrangement in the polymer structure of the monomers. This is because of both sterical electronic and steric reactions. Now, we are talking about radical polymerization and what are the different types of initiator we can use. Now, what is the source for initiator? We require a radical species to initiate the polymer chain, and we now will look at what are the molecules which, or what are the possible ways we can generate radical in the reaction medium. Now, to have a radical species, to generate a radical species in the reaction medium, you should always prefer, or it is very logical that the radical should not generate at in ambient conditions like room temperature, where you store this your monomer or the initiator itself. While storing it should not generate radicals, or it's the initiator molecule should not be such that it is very difficult, you require very high temperature to generate a radical from that initiator molecules. So, and also this radical the initiator molecule should generate radical in a moderate rate, so that they can be utilized in the reaction. It should not be very fast. If it is very fast radical generation, then the reaction will be extremely fast, and because this chain polymerization or exothermic, if the reaction is very fast, then you can imagine the amount of heat generated during the reaction, which could be a hazard. It can actually explode if the reaction rate is too high, and if it is too slow, then your reaction will take much longer time. If your radical generation is too low, then your reaction will take much longer time. So, the three criteria initiator should fulfill. One is that it should be readily available, of course, especially for commercial application it should be readily available, and it should be stable at ambient condition. If you are storing it in ambient condition at room temperature, or even if you are storing in a refrigerator, it should be stable in that condition. Okay, it should not generate radical under the condition of storage. And of course, the third one we just talked about, that it should generate radical in a practical rate at normal reaction temperature. It should not be too slow for the reactions to take much longer time, or it should not be too high, then there are possibilities of hazard because of exothermic reactions happening in much faster rate. So, what are the initiators or initiator procedure we typically use in a radical chain polymerization? First one is thermal initiator, and thermal initiator is a initiation by homolysis of a molecule by thermal energy, leading to formation of two radicals. And the typically here we are talking about homolytically cleaving one bond and making two radical. Now, the bond energy should be such that bond should not cleave at low temperature, at room temperature, or it should not be very high. The bond energy should not be very high, so that you require a much higher temperature to break that homolytically. So, the typical range of bond energy which are used for a initiator to be applicable as a thermal initiator is around 100 to 170 kilojoule per mole. And typically, if you have these peroxides or these SS bonds, or if you have NO bonds in your molecules, these bonds typically having bond dissociation energy of this range. So, they form on heating, and in normal the reaction temperature they form radical, each molecule form two radicals. For example, if we consider these peroxides, could be acyl peroxide, acetyl or benzoyl. For example, if I write the structure of benzoyl peroxide, it can break homolytically on thermal energy on heating to CO dot. Now, you can have alkyl peroxides as well. For example, cumyl or tertiary butyl peroxides. Let us take example of cumyl peroxide. It can dissociate into two such radicals. Also, these hydroperoxides, for example, tertiary butyl hydroperoxide, it can also undergo homolytic cleavage forming 2 radicals. Other examples also like PAR esters, let us talk about in the next page. For example, tertiary butyl phenyl benzoate, it can break from here and form 2 different radicals. Now, the other main type of initiator, thermal initiator, are azo compounds. For example, two dash azobis isobutyrylonitrile, which is most commonly named as or called as AIBN, which is having this following structure. Now, this can break into 2 species. Let us write in the next page. Plus N2. Now, in this case, the bond CN bond is not this bond is not of the having that bond dissociation energy between 100 to 170 kilojoule per mole. That is the bond energy, optimal bond energy we talked about. It is actually having higher 290 kilojoule per mole, but because of this nitrogen generation, this molecule, this dissociation also becomes feasible or very much feasible at normal reaction temperature. Other examples of azo compounds are for example 4,4 dash azobis cyanovaleric acid, so these are the examples, typical example of these azo compounds. Now, this compounds specialty is that it is water soluble at pH greater than 7. So, you can use this azo compounds at aqueous medium as well. So, that it can be used for generating or doing radical polymerization in aqueous medium as well, whereas AIBN can be used in the radical polymerization in organic solvents or organic medium. The other types of this radical initiator are like for example disulfides. I have RS and SR giving to RS dot, or I have tetragenes which breaking and giving to Rn to R2N dot plus nitrogen, or it could be other peroxides. For example, you have potassium I can have these peroxides as well. Okay, so, these are the typical examples of the radical initiators. These are the generally used radical initiator, and most common is EIBN and benzoyl peroxides, which are used in the lab. Now, this radical is gets generated from a initiator species. Now, if I want to find out how fast this radical generation happen, we can write this rate equation, which is basically dissociation constant multiplied by the, this follows first order kinetics. So, it is multiplied by initiator concentration, which will give you this on integration, where I 0 is the concentration of initiator at t is equal to 0, and this is some other t. Now, if you define t half, where a time where I is I 0 by 2, if you define t half as the time where the concentration of initiator has halved, then you can write t half is, you can put I is I 0 by 2, you can get this. So, from the dissociation constant you can get the t half value, and this dissociation constant also, or the rate constant for dissociation reaction also depend upon the temperature where you are doing your reaction. Now, if you want to do a reaction, and you should have prior knowledge about the initiator molecule, prior knowledge about their t half value or the time it takes to become half, then you can choose your reaction temperature, or if you want to do your reaction some particular temperature or a range of temperature, then you can choose the proper initiator for your reaction. For example, if I look at the t half values for the some commonly used initiator, for example, if I take very commonly used example like EIBN and benzoyl peroxide, say BPO, benzoyl peroxide, and if I write the values of t half, then let us have these numbers. So, if these are the t half numbers for commonly used initiator EIBN and BPO. So, EIBN have t half value at 50 degree centigrade about 74 hours, whereas at 100 degree centigrade it has a t half of 7.2 minutes. Okay. That means, if you use EIBN as the initiator for a reaction which you are carrying out at 100 degree centigrade, then your reaction is very fast, it will complete, and all the EIBN, at least half of the EIBN will consumed in 7 minutes. So, you can imagine your reaction is very fast, whereas if you do it at 50 degree centigrade, then even at 74 hours, so almost like 3 days you have half of the initiator is dissociated to form radicals. So, that means it is too slow a reaction if you do it at 50 degree centigrade. So, for that examples EIBN is typically used at say around 60 to 80 degree centigrade, and benzoyl peroxide typical reaction temperature is between 80 to 95 degree centigrade. And T half value for at 10 hours, the temperature at which T half value becomes 10 hours, it is typically the most what I say most used temperature, where T half is 10 hours, and for that EIBN is about 60 degree centigrade and BPO is about 65 degree centigrade, but it's all depends upon how fast you want to carry out a reaction. You have to choose your temperature accordingly. For example, EIBN, if you want to use 100 degree, it is too fast a reaction. So, it is always recommended that you should use EIBN at this range and BPO in and this range to have a moderate reaction rate. We have, and typical these values of KDs are typical values of KD for thermal initiator is 10 to the power minus 4 to 10 to the power minus 9 second inverse, and the usage range where your KD is from 10 to the power minus 2 10 to the power minus 6 centimeter. The temperature where your KD lies between these, that is the temperature where the reaction is typically done. So, we have now know that what are the molecules are typically used for thermal initiation, and what are the criteria in that initiator molecule should be, and looking at the T half values at different temperature, we should choose a temperature and a initiator combination for a particular reaction. If you want to do a reaction for a particular temperature, then you should choose a initiator molecule or a initiator molecule accordingly. So, now let us move to other type of initiator, and next let us look for redox initiator. So, let us look for redox initiators. And the name suggests if you have a reductant and you have a oxidants. So, for example, if you have a peroxide plus a this oxidizing agent, so plus a reducing agent. For example, you have a hydrogen peroxide plus ferrous salts giving to H2 minus plus H2 dot plus Fe3 plus. Instead of hydrogen peroxide, you can use the other peroxides or hydroperoxides as well. And in this case you can use other ions as well. Okay, these are the types you can use here and you can type here, but the general reaction is same, and the reaction is much faster and it can be done at room temperature or even at low temperature 0 to 5 degree centigrade or something. If you want to do a reaction at low temperature for whatever reason, then this is the initiator system you can apply, and as these things are soluble in aqueous medium, you can carry out the aqueous radical polymerization using redox initiator like this, or even if you want to do a your radical polymerization in emulsions, then also this type of reactions can be this initiator can be used. The other type of redox initiator, another example of redox initiator is persulfate and diamine plus diamine, again a combination of redox reducing and oxidizing agents. This is benzoyl peroxide and say an diethyl amine. If R is ethyl group, then it reacts and give this now Kd of this reaction is at 60 degree centigrade, whereas Kd for BPO at 90 degree centigrade was 1.33 into 10 to the power minus 4 second inverse, which means that this is much faster. This redox reaction is much faster. So, generation of radical by redox initiator can be done at much lower temperature, room temperature or even lower temperature, whereas in BPO the case of thermal initiator, the reaction rate is much lower. So, you need a higher temperature for doing the polymerization reaction. So, what we will do in the next lecture, we will continue this the other types of initiator, including the remaining example of the redox, the possibilities of redox initiator. So, we will come back and start in the next lecture from this redox, the other examples of redox initiators.